Hello. Here are some examples of concavity and points of inflection. So if you were given the function, for example, f of x equals x to the fourth plus x cubed minus 3x squared plus 1, and you would be asked either to find the points of inflection, discuss concavity, find the interval on which the function is concave up, something along those lines. But if you see those words, points of inflection, concavity, something related to them, you're going to be thinking second derivative. So our first derivative would be 4x cubed plus 3x squared minus 6x. Our second derivative then would be 12x squared plus 6x minus 6. We'll set that equal to 0 to find potential points of inflection. If this were a calculator one, I'd take the 12x squared plus 6x minus 6 and put it into my y equals to calc my zeros. If it was a non-calculator one, as this one is, we could factor 2x squared plus x minus 1. Just make sure to not add that 6 over. Do not add that 6 over. Okay. The 2x squared plus x minus 1 factors one step further to 2x minus 1, x plus 1. So I have two potential points of inflection, one at 1/2 and one at -1. To see if they are in fact points of inflection, I'm going to do a number line test here. My testing numbers are going to get plugged into the second derivative. So I'm going to test 1, 0, and -2. When I plug in 1, I get a positive number, so I know my original function will be concave up. When I plug in 0, I get a negative, so I know my original function will be concave down. When I plug in -2, I get a positive, so I know it'll be concave up. So I've got points of inflection at -1, -2, and 1/2, 7/16. I know they are points of inflection at -1 and 1/2 because this is where I see a switch in concavity, and I get the -2 and the 7/16, the two y coordinates, by plugging my x coordinates back into my original function, into my y up here. I also could say where I'm concave up, which would be on -infinity to -1 and 1/2 to infinity. And I'm concave down on -1 to 1/2. Okay. Let's go ahead and do a couple more. For example, I could be given y equals 1 over x minus 3. So again, I'll be thinking, where are the points of inflection? What are the intervals of concavity? So, second derivative. You could do quotient rule, or you could change this x minus 3 into x minus 3 to the -1 and make it a power chain rule. Either way, you're going to end up with a first derivative of -1 over the quantity of x minus 3 squared. Personally, I did get this one, just so you know where I got mine, from the chain power rule, which is turning this 1 over x minus 3 into x minus 3 to the -1, which means I brought down that exponent, -1, that's where that -1 came from, left the guts alone, subtracted 1 from the exponent, so -2, that's where this x minus 3 quantity squared came from, and then times the derivative of the guts, which is times 1. Which is not going to change my function at all. Okay, and then second derivative, I'll actually be getting my second derivative the same way. Although again, you could do quotient rule. But I'll go ahead and do power rule again, so we get -2 over x minus 3 cubed. Again, bringing down the exponent, leaving the guts alone, subtracting 1 from the exponent, times the derivative of the guts, which would be 1, which is not going to change my fraction. Okay, so where does this equal 0? Well, nowhere. -2 does not equal 0. -2 is -2. So I already know I have no points of inflection, but to discuss intervals of concavity, there is one other number that I do want to make sure that I've considered, which is where does this denominator equal 0? And my denominator equals 0 at 3. Again, this isn't because this is going to be a point of inflection. This 3, look at my original function up here, this 1 over x minus 3. If I plug 3 up in here, I get 1 over 0, which is not possible. 3 is outside my domain, so it's not going to be a point of inflection. It's not a point to begin with. But it could be a change in concavity. So we do want to test that one. So I'm going to go ahead and test 0 and 4. When I plug in 0, I get a positive, so I know my original function was concave up. Okay. And I just realized I made an error. Let me backtrack a little bit. I'm going to get positive 2 over x minus 3 here. Okay. My apologies about that. Let's make sure that it's clear why it's positive 2. When I bring down the negative 2, I have negative 2 times negative 1. I left off the negative out front here from this negative 1. You see that, rewriting it? So this should be negative x minus 3 to the negative 2. And bringing down the negative 2, we get positive 2. But then the rest of the explanation is still good. Okay, so let me retest this. When I plug in 0, I do not get a positive. When I plug in 0, I get a negative, and so I know my original function will be concave down. And when I plug in 4, then I get a positive, which will be concave up. And so 3 is not a point of inflection. 3 is instead a change in concavity. Concave, or I should say, is instead just a change in concavity. It's not a point of inflection. It's concave down on negative infinity to 3, and concave up on 3 to infinity. Okay, let's go ahead and do one more here. We'll make this one a calculator one. We have f of x equals 1/4 x to the 4th plus x cubed minus x squared plus 3x. It's a second derivative. My first derivative is going to be x cubed plus 6x minus, wow, I apologize. Let me back up. It's going to be x cubed plus 3x squared minus 2x plus 3. And then my second derivative, that's where the 6x is going to be, is 3x squared plus 6x minus 2. And where does this equal 0? Okay, so first and second derivative there. Okay, if this factored, I'd factor. Unfortunately, it does not. And so I am going to just have to either do quadratic formula or calc my 0 in my calculator. Don't add the 2 over though, right? We talked about that several times now. So if I go to my y equals, I can plug in my 3x squared plus 6x minus 2, this thing that I want to equal 0. I'm going to go ahead and make my window, we'll go -5 to 5. If I need to, I'll make it a little bit bigger. I know I should see a u. So if I don't see a u, I'd make my window bigger, but sure enough, I see a u, and I can see my 2 zeros, 1 here and 1 here. Right? So I'm going to go ahead and calc my 0. Okay, we have a left bound and a right bound and a guess. So I get 1 0 at negative 2.290994. And I have a second 0 if I repeat that process at 0.29099,445. Okay, so I'm going to test it into my second derivative. I'm going to go ahead and test -3, 0, and 1. Excuse me, sorry. Okay, when I plug in -3 in up here, I end up with 27 minus 18 minus 2, which is a positive, so I know I'm going to be concave up. When I plug in 0, I get 0 plus 0 minus 2, which is a negative, so concave down. And when I plug in 1, I get 3 plus 6 minus 2, which is a positive, and so I know my function will be concave up. And so I can answer all of my questions. I have points of inflection at negative 2.291, negative 17.259, and 0.291, 0.815. Again, x's, I know they're points of inflection because I see a change in concavity at both of these two x values, and the y's come from taking my two x's and plugging them back into my original function up here, this original f of x. I'm concave up on negative infinity to negative 2.291 and 0.291 to infinity. And I'm concave down on negative 2.291, 0.291. And there you go.